So we're going to talk about one property of independent random variables, and it's that if x and y are independent random variables, and let's say x is a continuous random variable with density f of x, and y is a continuous random variable with density f of y, then of course then we know that the joint density can be factored by independence as such. And the claim is that expectation of x times y is equal to expectation of x times expectation of y, provided that expectation of xy in absolute value is less than infinity. So this is like a condition that we satisfy for Fubini's theorem. So by the definition of expectation, the expectation of xy is x times y, the joint density of x and y, over the product space. And because Fubini's theorem is satisfied, we can actually express this integral as this integral, the integral over this space x, the integral over all the possible values of y, of xy times f of x times f of y dy dx. We broke down, we used the factorization theorem of independence over here. Right, so note that the integration variable is with respect to y. So x here and f of x here, they're both constants with respect to y. So we can factor them out like we did over here. So we're left with, for the integral with respect to y, we're left with integral over all the values of y times f of y dy. Now this you can identify as the expectation of y, right? So that's just the definition of y, expectation. And then, so this is now a constant with respect to x. So expectation is actually just a constant. So so the expectation of random variable is a constant. So expectation of y is a constant with respect to x, and we can pull it out, and we're left with e of y times the integral of x f of x. But this again you can identify as the expectation of x, right? So we actually we can prove the claim. Now, for this condition over here, or for this statement to hold true, you actually don't require that x and y are independent. So there are random variables that are not independent, random variables x and y that are not independent, where the statement holds true. And here's the example. So let's say x is a standard normal, right? And then y is equal to x squared. Then let's calculate expectation of x cubed, right? Because expectation of x times y is actually y is x squared, so this is going to be expectation of x cubed, right? So by definition of the standard normal and expectation, so we want to take this function x cubed, so this is x cubed, and then there's the density of the standard normal. Now if you don't immediately see this, this is actually equal to 0. And that's because this is an even function and this is an odd function, and you're integrating, so the product will be an odd function, and you're integrating this odd function over the real line, which is going to give you an integral of 0. If you don't know why this is an odd function, we'll do a short proof over here. So let's suppose that we have this function f of x, which is a product of two functions, g of x and h of x. And let's say g of x is odd and h of x is even, right? So x cubed here is odd, and the density, the standard normal density is even. So that's our h of x here. So f of minus x is equal to g of minus x times h of minus x. This is just by definition of f of x, right? So this is by definition. But since g of x is odd, g of minus x is actually equal to minus g of x. And since h of x is even, so h of minus x is equal to h of x. So this actually implies that f of minus x is equal to minus g of x times h of x, which is equal to minus f of x. So f is itself odd. So if you integrate an odd function over the real line, it's pretty simple to see that it's 0. For example, let's say you have a function that looks like, this. So this is sine. If you integrate sine from minus pi to pi, then you can see that these areas are equal to each other. So the integral is going to be 0. Right. So note that by definition of the standard normal, we have that the expectation of x is equal to 0, right? Since we took a standard normal, which has mean 0. So we have that, we showed that expectation of x cubed is 0. And this is also equal to expectation of x times e of x squared, which is equal to 0 times sigma squared. So this should be actually just 1, since this is the standard normal. But 0 times 1 is also 0. So the statement expectation of xy equals expectation of x times expectation of y, this is satisfied. However, x and y are clearly not independent because we define y to be x squared. So if you know x, then you have complete information about y. So they're clearly dependent, right? So if x is 5, then y is immediately 25. There's no other way around it. So these random variables don't have to be independent to satisfy the statement. However, there's a definition for such random variables. We called x and y uncorrelated if, covariance of x and y. So this is the definition of covariance. Covariance of x and y is equal to expectation of xy minus expectation of x times expectation of y. So we call these random variables uncorrelated if the covariance is equal to 0. And you can clearly see that this covariance being 0 is the same statement as expectation xy equals expectation of x times expectation of y, right? Because we just have to add this to the other side. Right, so for this statement to hold, for the statement above to hold, right, we only need that x and y are uncorrelated, not necessarily independent. And then note that if you have covariance of x and x, which are random variables, then we have that by definition of covariance, we just replace this y with x, right? And then this y is x here. So this is expectation of x squared minus expectation of x, quantity squared, which is just the definition of variance of x.